We touch our screens over 2,000 times a day. But what exactly are we touching? It is a highly integrated module, a stack of a dozen layers engineered to microscopic tolerances. What we perceive as a simple screen is actually a highly integrated module. It is a complex stack of distinct functional layers, precision engineered to work as one. By exploding the module, we reveal the core components: the protective cover glass, the capacitive touch sensors, the active display panel, and the optical adhesives that bond them together. Crucially, these layers are not made in one place. They are manufactured in separate, highly specialized facilities across the globe, ensuring the extreme precision required for each distinct task before they are finally fused into a single unit. The journey of cover glass begins with high-purity sand and specific minerals. These raw materials are fed into a furnace and heated to temperatures exceeding 1,500 degrees Celsius. In the fusion draw process, molten glass is channeled into a V-shaped trough called an isopipe. The glass overflows evenly from both sides, meeting at the bottom to form a single, continuous sheet. Because the glass is formed while suspended in air, it never touches solid surfaces during the draw. This creates a surface so flat and pristine that no mechanical polishing is needed. Glass surface strength is achieved through an ion exchange process. Initially, the glass surface is populated with smaller sodium ions. The glass is submerged in a molten salt bath containing larger potassium ions. These ions are forced into the surface lattice of the glass. The larger potassium ions replace the smaller sodium ions. Because the potassium ions are physically larger, they crowd the surface. This crowding creates a layer of intense compressive stress. This pre-stressed surface layer acts like armor, preventing cracks from propagating. By manipulating the glass at the atomic level, we create a durable shield for our devices. After the initial fabrication, the glass arrives as a massive sheet that must be divided into individual smartphone panels with sub-millimeter precision. High-energy lasers trace the cutting path. This thermal process vaporizes the material, creating a clean separation without mechanical stress. However, the cut edge is not perfectly smooth. At a microscopic level, jagged flaws act as stress concentrators. Edge grinding and polishing are critical. Removing these microscopic flaws is the only way to prevent catastrophic failure when the device is under daily stress. By perfecting the edge, we transform fragile glass into a durable, shock-resistant smartphone component. To ensure the screen remains smudge-resistant, we apply an oleophobic coating. Through vacuum deposition, molecules are vaporized and bond at the surface level, creating a permanent, oil-repellent barrier. This molecular bond results in low surface energy. Oils and fingerprints cannot adhere effectively, allowing them to be wiped away effortlessly. The shift to OLED technology has fundamentally changed how displays render light. Unlike traditional LCD screens, which rely on a constant backlight passing through liquid crystal shutters, OLED pixels are self-emissive. In an OLED panel, every single pixel acts as its own light source. When electricity flows through the organic material, it emits light directly. This eliminates the need for a backlight entirely. This enables true black levels. Because a pixel can simply turn off, it emits zero light, creating infinite contrast ratios that LCDs cannot match. The thin-film transistor backplane is the heart of every smartphone display. It contains millions of microscopic transistors that act as individual switches for every single subpixel. To create these, we use photolithography. A mask defines the pattern, and intense light sets the circuit architecture across the thin film surface. By precisely patterning these circuits, each subpixel can be switched on or off at lightning speed, delivering the high-definition imagery we interact with daily. In standard OLED displays, a single light-emitting stack handles all the brightness. Pushing this layer harder increases intensity, but drastically accelerates material degradation, leading to burn-in. The 2026 industry standard is the tandem structure. By stacking two light-emitting layers connected by a charge generation layer, we achieve significant improvements. This tandem arrangement effectively doubles potential brightness while allowing each layer to run at lower, safer currents. This dramatically increases device longevity and nearly eliminates the risk of permanent screen burn-in. OLED materials are incredibly sensitive. Exposure to oxygen or moisture causes rapid degradation, destroying the display from the inside out. To protect these layers, we use thin film encapsulation. This involves depositing microscopic barriers that seal the stack completely. The gold standard is atomic layer deposition, or ALD. This builds a perfect atomic barrier, layer by layer, filling every microscopic gap. At the heart of every smartphone screen is a hidden layer of indium tin oxide, or ITO. This forms a precise grid of conductive lines that constantly monitor the surface for human interaction. An electrical current flows through this grid, creating a uniform electrostatic field at every intersection. Because the human body is conductive, touching the screen disrupts this field. When your finger approaches, it draws a tiny amount of charge from the grid. The sensor detects this local change in capacitance, allowing the processor to calculate the exact coordinate of contact. Through this rapid triangulation, the device interprets your physical movement as a digital command, enabling the fluid interface we use every day. Modern smartphones use an innovative on-cell integration process. Previously, displays relied on a separate external touch sensor layer placed on top of the OLED module. This traditional stack added significant thickness and created unwanted refraction, reducing optical clarity. The shift to on-cell architecture embeds touch sensors directly into the OLED thin film encapsulation layer. By removing the redundant touch glass, we significantly reduce device thickness. This results in a leaner display stack, improving light transmission and overall durability by eliminating unnecessary interface gaps. Optical lamination is the critical process of bonding the cover glass to the OLED display module. We use liquid optical clear adhesive, or LOCA, to bridge these two layers. This process happens entirely within a vacuum chamber. This environment is essential to eliminate air pockets and dust particles that would compromise clarity. The components are pressed together slowly. The adhesive spreads uniformly, filling every microscopic gap without trapping any bubbles. Once cured, the result is a perfectly transparent, durable, and highly resilient display module ready for final device integration. In traditional displays, a significant portion of light is trapped inside the panel due to internal reflection, limiting brightness and wasting battery. Enter the microlens array. Billions of microscopic lenses sit atop every pixel, acting as a redirecting layer. These lenses capture light that would otherwise be trapped and focus it outward. This simple architecture increases peak brightness by 20 to 30% without any extra battery drain. Display manufacturing demands extreme purity. Even a single speck of dust can destroy the delicate microscopic circuitry of an OLED panel. Manufacturing occurs in specialized facilities known as clean rooms. To maintain precision, we operate at Class 10 standards. In a standard room, millions of particles float in the air. But in a Class 10 clean room, that number is restricted strictly. A Class 10 clean room ensures that no more than 10 particles larger than half a micrometer exist in a single cubic foot of air. This is achieved through continuous HEPA-filtered laminar airflow, which sweeps away any microscopic contaminants before they can settle on the glass. This level of precision is not just a standard. It is a physical necessity for building the world's most advanced displays. In smartphone manufacturing, yield is the percentage of display modules that pass stringent quality checks. The industry standard currently sits between 70 and 85%. Because the display module accounts for nearly 30% of a smartphone's cost, Even a 1% increase in yield efficiency can translate into massive profit gains for manufacturers. Standard glass is prone to cracks because its structure is uniform. When a crack starts, it travels unimpeded through the material. Ceramic glass hybrids revolutionize this by embedding nanoscopic crystalline phases within the glass matrix. When a stress point creates a crack, these crystals act as atomic shields. They deflect the crack's path, preventing it from shattering the entire module. The final stage of production is the integration of the display module into the device chassis. High-precision structural adhesives are applied to the frame, ensuring a perfect seal that maintains the device's durability. Crucially, these modern bonding materials are engineered to remain reversible, allowing for safe disassembly during future repairs. The display module is then lowered into position, locking the internal components securely within the phone's housing. This precision assembly completes the manufacturing cycle, turning thousands of components into a single, functional device. Sustainability is a growing priority in the electronics industry, specifically through the design principle of circularity. Standard manufacturing often uses permanent adhesives that make recycling difficult. The industry is now shifting toward reversible adhesives. These innovative materials allow the display module to cleanly separate from the device chassis at the end of its life, preventing damage to sensitive components. This enables efficient recovery of valuable rare earth elements, reducing waste and supporting a more sustainable production lifecycle. So, what does this all mean for you? Every time you glance at your phone, you are looking at a masterwork of human ingenuity. From the molecular level of OLED deposition to the microscopic lens arrays, thousands of invisible, high-precision steps have brought this image to life. It is truly a piece of high-tech art, existing at the intersection of extreme precision and daily utility. Keep exploring the science hidden in your pocket.